SwayamPrabha. Digital India. Educated India.
Welcome back. In lecture 20, we will cover the second part of microsimulation and population synthesis. In this lecture, we will cover iterative proportional fitting for a three-dimensional table. We will detail out synthetic reconstruction, combinatorial optimization technique, and we will touch upon some other methods for generating a synthetic population. So, when we talk about a three-dimensional table, in the previous lecture, we were discussing about two-dimensional tables. So, if I increase that by one more dimension, dimension is like the number of variables that we used in a classification table. So, in a 2D table, we had gender, if we can have gender and income, and two-dimension tables have got two single-dimensional variables or marginals. So, that means both the marginals are of single dimension, but in a 3D table, that means in a three-dimensional table, when we have got gender, income and education, three variables. So, we have got three sets of marginals like a cube, and that also means that we have got three two-dimensional marginals. That means we have got marginals for gender and income, gender and education, and income and education. That means we need to understand for each of the population group for a particular gender and income level, what is the number of people, what is the control total for that, and also the seed data for that. Then gender and education, for that we need to have, then income and education, for that we need to have. The seed needs to be three-dimensional, where we have got the data for both gender, income and education. All the three things has to be there in the seed. And this could be referred and as rows, columns and also slices. So, in this particular image you can see in the three dimension, this data could be represented as a cube. That means it is not only in two dimensions like a row and a column. So, we have got rows, columns and slices, and we have, when we take this particular cube, take it apart, we can see that there are we have marginals for rows, we have marginals for columns, and then we have marginals for slices, and we have seed tables. Like over here we have two seed tables for two slices, slice 1 and slice 2. So, I will explain that in detail using an example. Over here in this particular image, you can see we have represented the same data. Instead of a cube form, we have represented that in a format which is more easily understandable. So, we have got rows, columns, and then we have got, we can call it a slice, or we can call them a slice, column, row, any way we can call it. So, we have income, we have gender, we have education. These are the three variables that we are talking about. So, in the first part, this blue part is the three-dimensional seed. That means for each row, row 1, column 1 or income level 1, gender of first category, education level 1, this is the value. Then this one is the same row, same income group, same gender, for education level 2, what is the seed, and so onward. So, this is the three-dimensional seed that we have got. And then we have got control totals. We have got three two-dimensional controls. That means for row 1 and column 1, that is income level 1 and gender level 1, this is the first control. So, all the grays are two-level controls, two-dimensional controls. So, over here in this particular, this first marginal is for rows and columns like income and gender. These are the marginals, two-dimensional marginals for income, gender. And then over here, income and education, these are the, these gray cells are the, again the two-dimensional marginals. That means for each income level and each education level, we have a marginal value. Again, we need to make sure that all marginals should be consistent, because they should add up to the total value. which is 143 in this particular case. So then for over here, for each gender group, there are 2 gender groups and then there are 4 education levels. We have got this again, these are the marginals. So gender group 1, for education group 1, this is the marginal value. So these are the different marginal values. So we need to know these marginals for a target area for this part and this part, then only we can predict for the that particular zone, that what should be the 3-dimensional with this kind of 3-dimensional data for that particular zone. Demographic groups, like we need to have income, gender and education for each of those zones. For each of these groups, we can predict the number of households or in that particular zone using this particular, if we have the marginals for all these groups. And these yellow ones are the totals for single dimensions. That means 40 is total number of people of education group 1. 38 is total number of people of education group 2. Similarly, 38 is the total number of people in income group 1, and gender is 76 is the total number of people in gender group 1. So all of them should also add up to 143. Now, as we have done in the previous IPF, we need to make sure that each marginal is adjusted proportionately one at a time. That means this seed data has to be proportionately adjusted as per each marginal. That means first we should take this, then we should take this, and then we should take this. That means in step 1, adjust each row of cells proportionally to match the target totals of marginal 1, which is income gender adjustment. So we adjust for income and gender, this one, and using this value we can add up this seed value and then we can see the target value. This is the target value, and then we can take the proportion and we can multiply the seed and we can get a new estimate for this particular for each of this demographic group, the number of households. And similarly, in the next step, adjust each column of cells like proportionately to match the target totals of marginal 2. That means using this marginals, we need to adjust again the total data, and this could be called income education adjustment. And then we have got marginals in the target, and multiplying this with that, dividing this with that, we can also get a proportion, and then we can multiply with this to get to the final values. So similarly, adjust each slice of cell like gender education adjustment to match the target total of our marginal 3. And we will then repeat steps 1 to 3 till convergence is reached. In the same way we did the previous IPF of 2 dimensions. So in this example, you can see if I am using the same example from the last slide. Here you can see we have got in the target area, we have got marginals for income and gender, we have got marginals for income and education, these are the ones, and then we have got marginals for gender and education. Now, what we are in the first step, what we have done is we have taken the value for this is the target value 30, and this is the summation of the first row, and we have found the proportion and then using that to multiply with this value, we found that 30 divided by 22 is now multiplied with 5 and we get 6.818, and we do that for all the rows, and we keep on doing that for all the rows, and we get a updated table where we are getting values where all the first marginal matches. That means this matches with the target, but none of the others matches, but 10.757 is not same as 12. So we need to match this with this. So in the next step in marginal, in the next step, we again adjust this particular values by multiplying it with the proportion, where we multiply by over here we have got 10 and here we have got 12. So we will multiply by a fact, we will increase this is the target. So target divided by summation of this particular value, we can find the proportion, and then we can multiply with this is income level 1. So, we will multiply with income this particular row, this particular column we can multiply this we will multiply, and then for income level 2 we will multiply this values and so on, and then for this particular one we will see divide 14 divided by 13, and then we will multiply that with here 1, then again over here, and in the next for this value 2, income group 2, we will multiply over here, and income this group we will multiply here and here. And same way we can also do it for, once we do that, we see that this marginal matches, all this marginal matches with the previous one, but with the target, but this one don't match. So, over so this one and also this one will not match now. So, in the next step we will match this values. We will see this is 27.95 and we have got 28 as the target. So, again 28 divided by 27.95, we will multiply that proportion with the values in this table, and we can get this new values, and here we see that this marginals again match, but this two does not match. So, we will keep on iterating this again till the point when everything is to our expectations and the differences are not that much, and we can stop it there. So, this is how a 3-dimensional table could be also we can use a 3-dimensional IPF as well on our data to generate the cross classification tables for a particular zone. Now, one major problem with IPF is called the zero cell problem. Now, as we have in this particular figure, we have in this particular image we are seeing that all the cells have got some values, but some of these cells could have zero value, because in actual case when we have got different demographic groups, which is not only income, gender, education, but it may have many other variables, then the total number of people in each group is very less. So, over here it may turn out that many of those categories cells does not have any kind of seed data. So, not all categories are represented in the seed data. The zero value in the seed of this category leads to problems due to division by 0. So, because in IPF we have to divide each of the cells, and then sometimes it may lead to a zero value, and this is there are 3 ways to get around this problem. Either we can replace the 0 cells with a small value which is like 0.001, or we can use we can do something like category reduction, which is taken care in, which is done in PopScene and SEMDEP, this software as a pre-processing step. Before we even start the IPF, we can reduce the number of categories or the number of disaggregation that we are trying to, and these categories can be automatically aggregated considering a user specified threshold for marginals. So, we can do it based on certain criteria, like at least some amount of data should be there in each of those particular cells, and category reduction could be also done as an independent step to improve results. Sometimes too much disaggregation does not help, that means the data becomes too little. So, there also increasing the or reducing the number of categories also could be done as an independent step as well. In the final solution could be also another alternative way we can also solution is replace zone level seed using regional level seed estimate and the number of agents. That means we can take average values from the regional area, and we can also replace that with the particular seed value for this particular area, which has been done in PopGen. So, this is called the zero cell problem and how we can get around it. And then there is another thing called a sparse list, which I told which I mentioned earlier. So, what happens similar to the zero cell problem, with increase in attributes and categories, the complexity of categorization increases with several cells having 0 values, thus unnecessarily increasing the memory and computation load. That means, if we have many zones and we have many categories, that and we will see that we can have around 1 lakh categories, and out of that we will see that maybe 70,000 categories have got no values, whereas only 30,000 categories have values. So, if I do this kind of computations, then automatically we will see that there is it takes a lot of memory, the entire computation process becomes slower. So there has to be some alternative way instead of a matrix form. So this is where a list structure comes in, and a sparse list reduces memory requirement by considering a list based representation of attribute details, which is proportional to the size of the seed and the number of attributes and does not depend on categorization detail. That means for each of the type of this 30,000 groups or demographic groups or based on certain attributes or variables, we will be listing only those variables, and we can also write the number of individuals in those particular groups, which could be called as the weight of that particular group, and I will show that in an example. And instead we don't need to follow a matrix kind of structure. So we follow a list kind of structure, and each of this list could be like this weightage that we are getting. This could be again multiplied with, we can do classical IPF procedures by using an expansion factor, like that proportion that we had estimated in IPF, that could be multiplied with that particular weightage over there, and we can use it, use the list to do the same kind of calculations. And so in iLoot synthesizer, this is done where a classical IPF is added upon with an expansion factor, and a real valued expansion factor is attaches directly on the list of attributes for each of the items or each of the demographic groups, and that is how a sparse list works. So next, coming to synthetic construction or reconstruction of that particular population for that particular area, or we can call it allocation as well. So here while IPF helps in estimating the joint distribution of the different variables which are eventually used to build the models, that means we have cross classification tables and we determine the weights, proportions or actual values of each cell of this particular cross classification table using IPF, and then we adjust them to integers, and I already explained this process is called integerization or integer conversion, and there may be some problems arising because of rounding up, and but that means we can have first we need to determine the weights or proportion or values for each of those cells, or that means for each of the demographic groups, and then using this data we can create synthetic population of households or individuals also. So let us assume we are doing it for households, then we first need to select households from the reference sample in sample list. That means we are using a disaggregate sample that is called the reference sample. We need to select households from this disaggregate sample in proportion to the estimated probabilities given in the multi-weight table obtained by IPF or other techniques. So we can use IPF or other techniques. There are also other techniques for estimating this weight, proportion, values, but using this weight, proportion or values, we can estimate the probabilities, and we can based on these probabilities we can select the samples from the disaggregate sample set that we have got. So selection with replacement is more common than selection without replacement. That means if we have a sample list and we select one sample, we assume that in the next draw there is equal chance of getting that sample. But in many cases also we can use some measures through which we can take care of this by saying that, well, this particular group from where we have drawn a sample can get lesser chance of getting selected in the next draws. So that also could be done by attaching some extra weights to this particular probabilities. All variables essential for building the models also have to be written. That means even we have a cross classification table, so we can have multiple cross classification tables, and we can combine these tables when we estimate the probabilities by doing joint probability estimations, or we can only select some of the variables in a table instead of all variables in the table. Both is possible. So number of households in each type could be determined by total number of households multiplied by the probability in the multi-weight table as we discussed, and then household selection from the sample is done using Monte Carlo simple random sampling method using the conditional probabilities from the multi-weight tables. I will explain this, and this procedures could be sequential. For example, I am selecting households based on only age and sex. So we will determine the conditional probability of a household of a particular sex given a particular age. So that's a conditional probability. If I am doing it for age, sex and marital status, then we will say that okay, the probability of marital status with the condition that age and sex group is of a certain type. So using this sequential procedure, we can determine the probability of a particular group, probability of a particular sample to be selected, and then one problem is, if I instead of we do the same selection by saying marital status, then age and then sex, or we change the order to sex, age and marital status, then the results may vary. So this sequence also do play a role. Usually we will follow a sequence which is more based on the decision criteria in which that particular synthetic population is drawn for a particular model. For example, in case of a household, if I want to determine the mode choice, then probably first we need to determine the household head, then we need to determine if he is employed, then we need to determine if he is going to go to his office in a particular location, then comes the mode choice. So we determine the sequence in a particular order based on the requirement. Agents with higher probabilities appear more in the synthesized population. That is obvious, because the more probability or more number of chances, more probability you have got, the more number of, because we are following Monte Carlo simulation, you will be drawn more number of times. So in this example, we can see that this is a sparse list structure. So this table you can see over here is a sparse list structure where we have different household types, family and married couple. This is a family with married couple, and then non-family with female living alone, non-family with male living alone, then again family with married couple. So again family with married couple of household size 2, family with married couple of household size 3, family with married couple of again household size 2, and when these two are same, so these are different samples of the households that are available in a particular area or in my sample population. So this particular household is a married couple, it's a family, and it has a size of 2, this particular sample, and the weightage of 6 is basically means there are 6 of this type of households. So for example, you can see family married couple, again the weightage is 6. So if I draw this particular sample from this particular table, then automatically what happens, we can reduce this weight from 6 to 5, and that way we can record that okay, one sample has been drawn from this particular of this particular type. So this could be also used in a probability calculations in later on. But anyway, so first we have got this different sparse list for this different kind of households, and we also have their weight, and these are the different samples, and then we estimate each of their probability based on the conditional probability for this particular household. Like a household of size 2 given family, it's a married couple and it's a family, or the other way around, we can say probability of a household size of household type family married couple given a household size 2. Whichever way we want to do it, we can do that, and we can estimate conditional probability of an event in this particular way, where using this equation, where a conditional probability of an event B given that an event A has already occurred, this could be written as P with B given A, or probability of B given A, where we take this probability of A and B divided by probability of A. Probability of A and B means the intersection between A and B. That means where both A and B are present, the number of households where both A and B are present, and then this is the probability of A could be estimated from the total number of this A that is present. So that is A by the total population, A and B both are present by the total population, we get probabilities and we can estimate probability of B given A. So this is how we can determine conditional probability, or we can directly use the weight. From here also we can estimate the probability, like how many number of those particular group is there, we can use that if only these 2 variables are there. But if there were 3-4 variables over here, and for each we have got different weightages. So we know the control totals of each of these groups, and using conditional probability and the this intersection of those two groups, we can also determine conditional probabilities. So once we determine the conditional probabilities of each of this sample, we will list them like this, and then we determine the cumulative probability, like for example 0.089, then 0.1850. This is the probability of each one of this. We add them up, we get the cumulative probability 2.239. Then we have got 3, and then we add that, we get cumulative probability of 0.539. And then what we do is a random number is drawn from 0 to 1. For example, if I draw a random number of 0.705, then we see where this particular random number lies. We can see that it lies in this particular group, because the next group starts from 0.778. So that means we will say that household number 5 is selected from the sample. So that means this is the process of drawing a particular household from the sample, and then we will put it in the actual target area and then we will keep on doing that till in all the households or the total number of population for the target area is fulfilled, provided that the individual variables that for or individual characteristics of the household matches with the target area's total characteristics or that control totals for that particular target area. So that is what we have explained earlier in that steps of my fitting and allocation. And individuals of selected households form the synthetic population, and sometimes individual totals may not match. So this is that means even when household is selected and based on each household we determine the individuals, then of course the individual totals may not match with the area's control totals for individuals, but the household totals will match. But there are other procedures where both of them could be also matched by using different weightages or using both of them together and then giving weightages to both and so onwards. So this is the most simplest way to determine a sample or determine a synthetic population for a particular zone. There are many other ways where we can take both households and individuals together, or we can also have follow different weightage structures, like for example, because we are taking one sample from the from this particular population, then automatically chances of that particular sample to be drawn again has to be reduced. So that also could be incorporated. For that we can follow several procedures. For example, over here you can see probability of a particular household group could be determined as using conditional probabilities, as I have explained, or it could be a function which includes that conditional probability or the sample weight, or it could also include the number of expected households in the target area. That means based on the number of households in that target area, we can also, that may play a role in the total number of which sample can be drawn. And similarly, number of other households in the sample of the same group, that means the weightage of that particular sample, that also of that particular demographic type or that particular group in that particular sample, that the disaggregate sample, that also may play a role. So using all this, we can create a function of, or which should be used to determine the probability of a sample of getting selected. So in more complex softwares or procedures, this kind of techniques are followed. So thus probability. So what we can conclude is, for after every selection, the probability will get modified for the next sample selection. That means we need to recompute the probability after every selection, and that will also change the cumulative probability, and then again we have to draw another sample. So that means this probability is not done once, we will do it, but if I draw one, then automatically the weightages change, the probabilities will change, and again we need to recompute the probabilities. So this is a complex way, but this basic way is this one. So if this is followed, that also will give you a more or less correct synthetic population. So in conditional Monte Carlo, households and individual level multivariate tables are estimated independently. That means both the cross classification tables for households and individuals are done separately, and then individuals are assigned to households only in the allocation stage. That means when we select households and for a particular target area, then only we also look into what kind of individuals are being selected, and then we can match the totals for both, and then we can do the selection and of that particular household. And that is we do this in the allocation stage. And once households are selected, each member can be drawn from the subset of eligible persons as per the individual selection probability, thus ensuring consistent household and individual level marginal. So once households are selected, we can also do it stepwise. Then we can see that, okay, based on the type of individuals in that particular of these houses, we can select their probabilities, and then we can also ensure the selection. So these are the two variants that we can talk about. So once IPF is done, we also need to validate our results. The validations could be done internally or externally. Internal validation means if the same variables are utilized, that means the variables that we have used for synthesizing the population are also used to measure the errors in the IPF procedure. So that means marginals and cells are compared. So for the target population and our final results, all table cells are also used. That means the findings for each of the cells that we estimate, and with the actual figures, we can devise a goodness of fit for using all the cells. This kind of testing could be done. Then in case of simultaneous population synthesis of both households and individual cells, then both could be used to design an appropriate measure. That means if both households and individual populations are done together, then we can devise a new measure or goodness of fit where both things would be included. And then of course appropriate subcategorization. That means if we find that there are some errors, we can also find the right subcategorization of attributes which would give me the best possible synthetic population. And when we are talking about external validation, that means agreement between the synthetic population and the actual population from survey. But that means we have to have the data for the actual population. So here again marginal cells and tables are compared. But if we don't have actual population data to validate it, then we have to limit ourselves to internal validation only. So next, the method that we will discuss is combinatorial optimization. So this is less common than the IPFSR technique, but still it is used, and this was proposed by Williamsons in 1998. And we have found that in many literature, synthetic microdata using CO results in less variation among population. So this is a more robust procedure compared to the IPFSR technique, but of course it is more computationally intensive. And the population is synthesized zone by zone. That means we have to do it for each zone separately. We cannot do it for the entire city together, or the urban area or the region together. What is done is, initially a subset of individuals is selected randomly with replacement from the sample. That means we have the disaggregate sample. We select a subset of individuals from that sample randomly, and we need to see that the total number of samples drawn matches the population size for the zone for which we are selecting. So it could be households as well. It could be either sample of households, sample of population. So we will see that both of these matches, and we then determine that the fit of this list of individuals is assessed using the observed and expected cell counts of different tabulations. That means we will tabulate the different attributes or variables. Like for example, if I select 10 individuals, they have got age groups, they have got gender. We will tabulate each one of that. That means how many of male, how many female, how many of each age group. We will measure that, and we will also measure that for the observed, that is from the sample, and from the expected cell counts. That means what are the marginals for that particular zone, and we will do a statistics, a fit statistics. We will estimate a fit statistics using which we can understand how much different is our selected sample from the expected values. Then what we do is, one household from the sample that we have selected is replaced randomly with a fresh household from the sample data, and we keep on doing that one after another. But we need to check that when we replace it, does it improves the fit statistics? If it improves the fit statistics, we will retain the new household. Otherwise, we will return it back and then we will select another households from the sample. So, if fit statistics are improved, the households are swapped and the next iteration is undertaken. So, this is the general procedure of combinatorial optimization. I will show it with an example. And this have been further improved by Vos and Williamson using a sequential fitting procedure, where most difficult table is fitted first within a target. That means we have got several classification tables. The most difficult ones are first fitted and then the easier ones are fitted. So, this is the modified technique done by Vos and Williamson. So, here in this example you can see in step 1 we can suppose this is the list of my samples A, B, C, D, E are household samples, and these are the characteristics of that particular household sample, like size or household size, number of adults, number of children in that particular household. We can see that sample number A is of size 2, there are 2 adults, there is no children. Sample number B, there is size 2, adult 1 and 1 children, and so onward. So, this is the survey micro data or my disaggregate data. Then what we do is, these are the control totals for that particular target area. So, we know that small area and target or constraints, we can call them marginal, targets, constraints. And here we see that household size, we know that in the target area we have for household size 1 there is 1, and for household size 4 there is 1. This target area has got only 2 households, and similarly this target area has got 3 adults and 2 childs. So, this we know from the control totals for that small area. And you can see that this 2 household size of 2, household size of 3, there are no households, or even household size of 5 plus, there are no households. So, total number of households is 2, total population is 5. Then what we do is, households are selected randomly from the sample as initial micro data set for the sample area. So, as per the constraint, that means we know that there are only 2 households. So, that means we will select 2 households from my sample data, like over here I will select 2 households randomly from the sample, and we select A and E. Suppose these are the 2 samples which are selected randomly. And then what we do is, when we have these 2 samples, then these households are tabulated and absolute difference is calculated. That this absolute difference is the fit statistics that we were talking about. So, households are tabulated in this way. So, over here we have selected A and E. A has got size of 2, and that means household size of 2. We have given estimated frequency is 1. This is based, we are tabulating the selection that we have made. So, similarly, household size of 3, A and E, which is household size 3, we have also frequency 1. But in actual observed frequency, we see both of them are zeros, whereas observed frequency is 1 for household size 1 and household size 4 is also 1. So, absolute difference is 1 plus 1 plus 1 plus 1, which is 4. That means there are 4 cases of mismatch. So, this is the absolute difference. Absolute difference, because both both ways we are taking, positive and negative. And then in the population also, when we are looking at individuals, our selection of A and E results in estimated frequency of adult as 4 and estimated frequency of child as 1, whereas the observed frequency is 3 and 2 based on this table. So, here again there is absolute difference of 1 and 1, and so that means the total absolute difference is 2. And then we add up these 2 absolute differences. So, we have a total absolute difference of 6. So, in step 4, one of the pre-selected households is randomly selected and replaced with another randomly selected household from the sample, only if absolute difference is reduced. So, here we replace A with D. So, after we do that, we have seen that the total absolute difference comes down to 2 for the households, and for the population the absolute difference comes down to 1. So, total absolute difference is 3. So, we keep on doing this till there is no further reduction of this absolute difference. So, we see that finally D and C are my final selections for this particular zone. So, this is the process of combinatorial optimization for determining the synthetic population for a particular zone. So, now talking about some other softwares, or rather some other methods. In the albatross method, as we were discussing earlier in the previous lecture, our relationship matrix is created is used to estimate household composition that matches individual level constraint. So, this is a new method. So, unlike the IPF method, here our relationship matrix is first determined. Now, what does that mean is, suppose we take a contingency table of 2 by 2 columns, where these 2 by 2 columns include single and male female households, and we have the data in this contingency tables are couples, independent males, independent female, total male, total female. These are the data that is there in this contingency table. Now, we can add another row to this contingency table of 2 rows and 2 columns by addition by both at the row and the column side for including children for each of these categories. And then we can also disaggregate this by age and work status of the head of the household. So, this is, we can keep on increasing the size of the contingency table by disaggregating that as well. So, once we have this kind of a table where both the population as well as the household type is combined, that means both the data is available in the contingency table. That means in rows and columns we have got different types of data for individuals as well as families. Then we use matrices using the sample data, which could be used as seed for this particular matrices. We can undertake, IPF is undertaken on this relation matrices, and the whatever distributions we obtain based on this IPF are used as marginal for conducting IPF of household variables. That means, because we are following this particular structure that we observed in the seed for households as well as individuals in those households, and we are maintaining that in the overall population. So, automatically when we evaluate for households, automatically the structure, or rather the control totals of individuals, would also be maintained. So, this is a strategy followed in the albatross model, and this is called this is another way of doing this fitting, which is called a relation matrix. There is another method called iterative proportional updating, IPU, which is a variant of iterative proportional fitting, which is used in the PopGen software, where the IPU algorithm simultaneously control both agent, that is individual level, and agent group, that is household level attributes, by iteratively adjusting and relocating the weights. So, I told you earlier that both individuals as well as households could be simultaneously adjusted in a fitting exercise, where we can change their weights, and we can change based on the selection of a particular household or a particular individuals from that particular household. We can also do this iteratively, and we can determine the population group for synthetic population for a particular zone, and this is undertaken in the PopGen software. And the data structure followed is a tabular list of agent groups similar to the sparse list variation of IPF. So, basically we have got the agent group like households, we have got a tabular list, and for each of this household there is a population. In individuals are also there in each household. From there those lists would be also generated, and we can give weightage based on both the values, and then we can keep on modifying that. Then finally comes another process which is also getting popular these days, which is Markov chain Monte Carlo simulation, and this is also adopted for determining synthetic population for an area. In this approach, the focus is more on to meet the partial joint distribution of population characteristics rather than matching the marginal sums as in IPF. Like in IPF, we try to match the marginal sums at the end of the day, but here based on the seeds data, we see the partial joint distribution, that is how individual groups are, individual demographic groups, how many values are the weightages of each individual demographic groups. So, following those distribution, using those distribution and their dependencies, we do a simulation, which is not exactly a simple random Monte Carlo simulation. Here Joint distributions of population characteristics are considered, and these are organized as Markov chains. And in Markov chain Monte Carlo sampling method, samples are drawn such that the next sample is dependent on the existing sample. So that means there is conditional probability is considered. That means based on selection of a particular sample, particular attribute of a particular sample, the next attribute's chances would be different. And so it creates a chain of selections. So that's why it's called a Markov chain. And there are two algorithms. One is called a Gibbs sampling and Metropolis-Hastings algorithm, which are popular approaches to do Markov chain Monte Carlo sampling. So this is another upcoming method which is also used in many new methods of approaches of synthetic population creation. So these are some of the references you can follow. So to conclude, we can say that in India, since microsample data surveys are not conducted by the government, we need to collect extensive sample data sets for each study area, which is a major limitation in developing disaggregate models or conducting microsimulation studies. Then while several software has been developed for population synthesis, most are custom built for specific purpose and geographical context. None exists for India, so we need to develop this kind of software so that we can adopt microsimulation procedures, or we can do detailed land use transportation models where we can use disaggregate models. And then IPF could be used for developing cross classification tables for agents and agent groups for an urban area, which could be used to develop disaggregate models. And again, once we have got cross classification tables based using IPF, we can use that cross classification data to run discrete choice models to create more to predict values for other variables, which can also be added into the IPF procedure, and we can have more categories or more cross classifications. Then IPFSR and CO techniques are popular and easy methods of population synthesis which could be easily adopted. Thank you.